Hello, so in this video we're going to look at quantities and units. So units basically like kilometers, meters, seconds, stuff like that, right? Literal units to represent various stuff like time and distance. What we're also going to look at are forces. Okay, the main forces you need to be aware of for this course for mechanics, right? And I've got the first few here. So firstly we have tension. Now tension is in ropes and strings. So in this example here we have a box, right, that's being pulled up or held up by a rope. Now this rope is being, if you imagine, being tugged by someone. Someone is pulling the rope up, right? So what happens is if a rope is being pulled or stretched or held by something or someone, there's a force in the rope, okay? And this is a tension. So there's a tension force in the rope that's holding this box up, okay? So the box is being held up by rope, and obviously the rope is being pulled up by someone, okay? So when a rope is being stretched or affected, it has tension in the rope. So that's a force in a rope or a piece of string. Now this going down, now obviously let's say this box is in the air, obviously it's being held up by this rope, by the tension in the rope. That's the force in the rope that's holding the box up. But what's pulling it down? This is weight, okay? So, the force that pulls an object down is weight. Now weight, do not get confused with mass. The weight of someone or an object, the weight is not the number in a scale, like how much you weigh, I guess in normal terms. That's mass, okay? Mass is kind of the number on the scale, the physical number, how much size something is, I guess. Weight is the force that pulls you down. It's the force that pulls you down according to your mass, okay? So the mass is kind of how much you weigh, I guess in normal terms, from the scale or something like that. But the weight is the mass that you had that pulls you down, okay? Weight is a force, mass is just a number, okay? So I'm going to say weight, not mass. Do not get confused between the two, okay? We will look at this in more detail. We will look at weight and mass later on. But for now, it's the weight that pulls you down, and weight is not a number on the scale, the masses, okay? Okay, then in this example here, then the next one, we have a box on a sloped, right, a sloped piece of wood, a plank. Now obviously because it's slanted, the box it will move down, right? You can visualize that. The box would want to move down because it's sloping downwards, the plank. Now because the box is moving down, what happens is when something like a box here, an object is interacting with another surface, so in this case the box with the plank of wood here, when the box is moving down, it creates a friction force with the surface, with the wood here, which opposes or is opposite to it moving down. That is friction, okay? Friction occurs when an object is moving one way, so it's moving down here, so friction acts the other way to kind of slow it down, okay? The best it can, but that's friction. Okay, then we got this example here. Now again, now we have the box, right? But the box is now perfectly still on a table, right? It's not moving anywhere, it's staying where it is. But again, what's happening is the box really should be pulled down by the weight, right? The weight of the box will pull it down, kind of like gravity. The gravity of the box will want to pull the box downwards towards the floor, because of this force here that's dragging it down. But why is the box not moving anywhere? Surely if it's just weight, the gravity, why the box would surely just go through the table, right? And And think about it, if you're like sitting on a chair in a classroom, you don't just sink through the chair or sink through the ground, do you? There's something clearly, another force. It can't be just weight. That's kind of, that avoids you just sinking through the floor, right? There's another force called a reaction force or a normal reaction force that opposes the weight, okay? So a normal reaction force, or we just call it a reaction force, okay? And so a reaction force arises to stop the weight that just pulls you down, okay? So you don't just fall through the surface, if you will, right? So a reaction force arises when one object, so in this case the box, again it's on a surface, right? It's on top of this wooden table surface. So when an object is on a surface like this, there's a reaction force, okay? So when an object like this box is in contact, or what we say basically meeting with the table here, there'll be a reaction force that opposes the weight, okay? So to avoid it just sinking through the table, okay? So it isn't dragged down, it's held where it is, okay? That's a reaction force. Right. Okay, so now we've got this example here with a skydiver. So again, the skydiver falls down to the ground, it's in the air. Obviously the weight of the skydiver will pull it down. But because when things move through the air, or passes through the air, there will also be air resistance, kind of like friction, right? As it moves through the air resistance will try to oppose your motion the best it can, right? So if you move through air, so if the skydiver's coming down, okay, because of the weight's being dragged down, it falls down, right? It falls down. Air resistance will act up to kind of oppose the motion, okay? And you can kind of feel that if you're, for example, if you're driving a car, or you stick your head out or your hand out, you'll feel like a huge slap of air, like a big slap of wind as you stick your head out. That's air resistance. That huge like thud of like air that hits your face, that's air resistance as it to kind of like which tries to slow you down as you move through the air. Okay, talking about cars, we have this next example here. Now, this force here, what's this force saying? Well, obviously a car moves forward because the engine obviously works. The machinery in the car propels it forward. Okay, so obviously you hit the gas pedal, you accelerate, you move forward. That's the engine, but the engine in the car more specifically is creating a force to move you forward. That is a driving force. Okay, so this forward force is a driving force. You might also hear it be called a forward thrust. Okay, same idea. A driving force propels you forward. Okay. Okay. And it doesn't have to just be a car or anything mechanical. It can even just be people. If you're walking, for example, if you're walking, obviously your muscles contract, which allows you to walk and run and move forwards. But more specifically, the muscles contracting then generates a driving force that allows you to push and walk forward. Okay, and so there we are. Now with a car as well. Because it's on a road, it's on another surface, you might experience friction as well again. So friction, as you drive forward, friction will try to slow you down as you move throughout the road. And obviously a lot of friction could be bad for your tyres and stuff like that, but there is friction that kind of slow you down and oppose you driving forward. Likewise, air resistance. Obviously the car is driving through air as well. As a lot of things are. Even if you're running, you'll feel air resistance as well. Especially if it's windy, you'll feel more, like a gust of wind that might slap your face or something like that. Air resistance as you move through the air again will try to oppose your motion as well. Okay, so obviously you're going to need more power, more driving force to propel you forward, but there we are. Cool. Now this last example here, not really a common example. I wouldn't make a huge effort to be aware of this, but again, maybe you're expected, I guess, to know it. But we're in water. Okay, we have a boat. Now again, we have weight that's trying to pull the boat down. The boat has a mass, right? Has a weight that's pulling it down. But the problem is, unlike the example here with the table, as we discussed, the table, right, is a solid surface. We have a reaction force that's holding that's holding the box on the table, so it doesn't just fall down the table due to weight. There's a reaction force on a solid table. The problem here is we don't have a solid surface the boat is on. It's on water, right? It's a liquid, it's a fluid. That therefore means it cannot be a reaction force that keeps the boat up in the water. It's a buoyancy. So a buoyancy is kind of like a reaction force that keeps the water from drowning or sinking, but in water, okay? Because water isn't a solid surface, okay, like a road or table. So buoyancy is the sort of reaction force, but for boats or for stuff in water or liquids or fluids, right? Okay, and that's really the main forces to be aware of, and to be honest, the main forces we will be working with in mechanics are the first three examples here. Make sure especially you're comfortable with these first three examples, with weight, with tension, with friction, with a reaction force. Those are the four main forces we will be working with in this course. Okay, let's have a look at it. Okay, what we also need to be aware of are to do with units, in particular SI units. Okay, now SI units, you can see in this black table here, obviously a list of units or quantities. These are what we call the fundamental units. So they're kind of like base units, right? The most fundamental basic units to describe various things. So for example, length, we have meters. For time, we have seconds. For mass, we measure in kilograms. For electric currents, we have amps. So that's to do with circuits, electricity. You might be familiar with that from physics, GCSE. Temperature, Kelvin. So that's kind of like degrees Celsius temperature, but Kelvin is a different type of measurement that we use. Mole is we have a mole to do with amount of substance. So how many particles are in some sort of molecule, for example. That's to do with chemistry. And then we have candela, your last unit. That's to do with luminous intensity, so the light of something, right? The light, right? And so these 7 units, these 7 fundamental units are basically internationally agreed upon by scientists, mathematicians. So whenever some scientist does work with these units, or with units to do with weight, or to do with time, they want to aim to use these particular units here. The idea is once these 7 units are established, we can work out other quantities and convert them into these base units. For example, we should remember that if we had kilometers, right? If we have a kilometer, obviously kilometer is to do with length, it's to do with distance, but here, that's the standard is meters, right? We don't want kilometers, we want to convert it into meters. So what we do is, obviously we should know that 1 kilometer goes to 1,000 meters, and so that is the unit we want to use. We want to use 1,000 meters rather than 1 kilometer. Okay, they're the same thing, but we want to stick with meters, okay, as a unit of choice here. Right, and so yes, so in particular, we don't need to know all 7 of them. You just need to know for the mechanics these 3 here. So mass, which is kilograms, length, distance is to do with meters, time in seconds. Okay, so kilograms for weight, for mass, meters for length, and seconds for time. Okay, we want to convert it to these 3 different units if we can, right? And then any other unit we can convert into these units here. So about converting, then we can convert. We're asked to convert these quantities into SI units. You can think of these as sort of base or standard units, if you will. Okay, SI units, sort of standard units. Okay, so for kilometers. Now, kilometers, obviously to do with length, we want to convert that into meters, right? So we should be aiming for meters, kilograms, or seconds, right? So here we want to convert kilometers into meters because meters is the standard length unit. Okay, so again, as you should remember, 1 kilometer is going to be 1,000 meters. So therefore, 4 kilometers is going to be 4,000 meters, right? Then for part B, we have 0.32 grams. So grams isn't a standard weight mass unit, but kilograms is. So we want to convert grams into kilograms, right? So kg. Now, again, you should know that to convert 2 grams to kilograms, that 1 kilogram is 1,000 grams. Again, by the way, the reason for that is because kilograms or kilometers has kilo in the name. A kilo means 1,000. So 1 kilogram is 1,000 grams, literally, right? By word translation. So kilos 1,000. With that in mind, if we want to convert 0.32 grams to kilograms, we will need to divide by 1,000. So 0.32 divided by 1,000 is going to be 3.2. times 10 to the minus 4, and that's in standard form. That's what the calculator would get you, or as a decimal that should be 0.00032 kilograms. I believe that should be right, but that's the conversion into that. Okay, and then part C, we need to convert 5.1 times 10 to the 6. Now we have kilometers to the h to the minus 1. Okay, we need to convert this into SI units. Okay, so what we've got here is obviously a bit more complicated. We've got 2 different units. This is a compound unit, what we call it. So what this is saying is, well, firstly, h to the minus 1, if you just think, I guess, in terms of power laws, right, you should know that any number a to the minus 1 is the reciprocal to 1 over a. We can do the same here. So it's 5.1 times 10 to the 6 kilometers over h. Now h is hours, okay? Hours. So what we could do here then is, what this is saying is, by the way, this is saying kilometers per hour, I should say. So km per hour, okay? So the fraction means per, okay? So kilometers, then per, then hour. It's very similar to how we could, in GCSE, you might be familiar with meters per second. You might be familiar with that as meters per second in this way. This is a fraction as well, okay? This is literally, this slash, this per, is a fraction. It's the same as meters over seconds. It's what we've got here, right? That's what we're saying. And again, meters per second, in terms of powers, is ms to the minus 1. Because s to the minus 1 is over s, we're divided by s. Because it's reciprocal, okay? So, in A level, we don't use this notation anymore, meters per second. In that slash, we use indices, okay? So, the negative power being the reciprocal. Anyway, so we've got kilometers over hour. Now, what we can do at this point is, we obviously want to convert the kilometers and the hours, right? So the kilometers needs to go to meters, and the hours needs to go to seconds. Those are my SI, my standard units. So what we can say is, let's just focus on the kilometers over hour, right? Kilometer over hour. What we want to convert that into meters and seconds. So what we can say is equate that to meters over second. So we convert the kilometers on the top to meters, and then on the bottom we have hours. So in the new unit it'd be over seconds, okay? Now, let's say we have 1 kilometre over 1 hour. Now, what we want to do is physically convert, firstly, 1 kilometre into metres. Now, you should know 1 kilometre is 1,000. Actually, I'll do it down here. 1 kilometre, 1 km is 1,000 metres. Therefore, we can say 1 kilometre is 1,000 metres here. Okay. Now, on the bottom, we have 1 hour. But we have seconds. We need to convert 1 hour into seconds. Now, you probably won't know that directly, but what we should know is 1 hour is 60 minutes, okay? We should know that. What we should also know is 60 minutes is 1 minute, sorry, is 60 seconds. Therefore, every minute is 60 seconds, so 60 minutes will be 60 times 60 seconds. Therefore, we could say that 1 hour, if we do 60 times 60, that'd be 3,600 seconds, okay? And that is my conversion. So sometimes you might have to kind of work out a conversion in that way, if you're not sure. So therefore, 1 hour here will be 3,600 seconds. Okay, that is sort of my conversion, okay, here. And actually then at this point I could just simplify the fraction. So if I do then 1,000 divided by 3,600, I get 5 over 18. That simplifies to 5 over 18 meters over second. Okay. So this is sort of then a conversion factor, this number here. So if I want to convert then 5.1 times 10 to the 6 kilometers per hour, I can then do 5.1 times 10 to the 6, not kilometers per hour, but because that's the same as 5 over 18 meters per second. So now at that point, I just times the number by my conversion by 5 over 18. So if I do 5.1 times 10 to the 6 times by 5 over 18, I get 1,416,666.67 ms to one decimal place. And actually, meters over second, I can then write that as a power to meters to the s to the minus 1. That means meters per second. Okay. And there we are. Okay, so that's the idea. When we have a sort of a compound unit, 2 units together, we can write it as a fraction like this and then convert them one by one in this way. Okay, so we're going to practice some more on this. So firstly, we have 65 kilometers per hour. So again, what we can do firstly to help me see what to do is to convert this unit here as a fraction, right? Because h to the minus 1 is a fraction. So this is 65 kilometer over h, over hours, okay? And so again, what we can do here is, well, then we can just convert the unit part, this fraction kilometers over hour. So kilometer over hour, obviously the kilometer needs to go to meters, so that'd be over meters, and then h needs to go to seconds, okay? Now, as we just discussed up here, 1 kilometer is 1,000 meters, so km is 1,000 meters, and then 1 hour is 3,600 seconds, okay? And then we can simplify it and we should get 5 over 18 meters per second, okay? M over s. So therefore, this is sort of my conversion now. So if I do 65, so 65 lots of kilometers per hour is 65 times 5 over 18 meters per second. Then if I do 65 times 5 over 18, I get 18.1 meters per second to one decimal place. And again, I can write that as a power in power laws, meters over second, ms to the minus 1. Okay, and that's my conversion. Part B, we have 15 grams per centimeters to the minus 2. Okay, So what this is saying is 15 grams divided by centimetres squared. Okay. Again, then we want to convert this double unit here, this fraction, these two units here, grams and centimetres, into standard units. So grams per centimetre squared. We want to convert that into, well, grams firstly needs to go to kilograms. And centimetre squared, well, meters, right? That'd be meters squared, right? Forget about the squared bit. Physically, just focus on the centimetre bit. We want to convert that to meters, right? And so, well, 1 gram then. So 1 gram over 1 centimetre squared. Well, 1 gram. Well, you should know 1 kilogram is again 1,000 grams. So if we want to go to 1 gram, we need to divide by 1,000 each to get 0.001 kilograms to 1 gram. So 1 gram to kilograms is 0.001. Okay. Now, centimetre squared to metre squared. Well, again, we want to convert 1 centimetre squared into how many metres squared. This one's quite tricky. Now, we can't say, well, we should know 1 metre is 100 centimetres, right? Now, it would be wrong to say, therefore, if we divide by 100, let's say, that 0.01 metres is 1 centimetre. That would not be then 0.01 metres squared. It's because the squared is complicating things. The way to think about this, when we're dealing with metres squared and centimetres squared, right, if we're squaring the units, let's think of it like this, okay? So, think about a... let's think about a square, right? Now the area, let's say it's 1 centimetre by 1 centimetre. The area would be 1 times 1, that'd be 1 centimetre squared, right? Now, let me now think of the same square, but instead of 1 centimetre, we're going to convert that into metres. So we should know, again, that's 0.01 metres, right? 1 centimetre means 0.01 metres by 0.01 metre. The area in this case is going to be 0.01 times 0.01. That would be 0.0001, I believe, metres squared, right? That is my conversion, because the two squares, the squares are the same, just that we converted the units differently of the length. So that means the two areas are the same. Therefore, we can deduce that 1 centimetre squared is 0.0001 metres squared. Alternatively, another way to visualise that 1 centimetre squared is 0.0001 metres squared without this whole square business. Well, again, note that 1 centimetre is, again, 0.01 metre. Again, that stems from 100 centimetres is 1 metre, so divide by 100. What I can do with this sort of equation here is I can sort of square both sides. So 1 centimetre all squared is 0.01 metres all squared. So then that'd be 1 squared centimetre squared is 0.01 squared metre squared. Well, of course, 1 squared just 1. So 1 centimetre squared is, well, 0.01 squared is going to be 0.0001 metres squared. There we are, we got our conversion. So 1 centimetre squared is 0.0001 metres squared. Now we can simplify this fraction by doing 0.001 on top by 0.0001 on the bottom. That simplifies to 10. So 10 kilograms over meters squared. That's my sort of conversion factor. So now 15 grams per centimetre squared into kilograms per metre squared. That's going to be 15 times 10 to the kilogram over metre squared. And so if we simplify that, that'd be 150 kilograms per metre squared, right? And there we are. Okay, so now we have part C, and it wants 30 centimeters per minute into SI units. So firstly, per minute, we can say that's 30, the same as 30 centimeters per min, right? Per minute. And then we, okay. Now, first of all, centimeters, we want to convert into, well, centimeters per minute, right? That's the units we have. We can convert firstly as the centimeters part. We want to convert that to meters. But then minutes, we want to convert that to seconds. Okay, so meters over seconds. Now, firstly, centimeters. Again, you should remember that 1 meter is 100 centimeters. Therefore, 1 centimeter is going to be 1 divided by 100 meters, or 0.01 meters. Okay, as we discussed just. So that's 0.01 meters. And then minutes, again, you should remember that 60 seconds are in 1 minute. So therefore 1 minute is 60 seconds. That's my conversion, right? So then 0.01 divided by 60 is 1 over 6,000 meters per second, or 1,600, 1 over 6,000 meters per second. Okay, and so this is my sort of conversion, right? The factor, if you will. So then this 30 centimeters per minute is 30 times 1 over 6,000 meters per second. Okay, if I work that out, I get 1 over 200 meters per second, or as a decimal, 0.005 meters per second. Okay. Now we have part D. Part D is saying 24 grams per meters to the -3. So again, as a fraction, that's 24 grams over meters cubed. So again, we want to convert grams over meters cubed into, well, grams we need to convert to kilograms. Now meters, we're already there actually. Meters is the unit we use for length, meters. So that's actually great. We don't need to do anything to that. That's great. So, but kilograms, well, again, we should note that 1,000 grams is in 1 kilogram. So 1 gram is going to be 0.001 kilograms if we divide by 1,000. So that's 0.001 kilograms over just 1 meters cubed. Okay, so then 0.001 divided by 1 is, well, just 0.001, right? Kilograms per meters to the -3. So this is sort of my conversion factor then. So this 24 then needs to be 24 times 0.001 kilograms per meters to the -3. And if we work that out, that's 0.024 kilograms per meters cubed. Okay, part E, we have 4.5 times 10 to the -2 grams per centimeters to the -3. So kilograms per centimeters cubed. Again, we can write this unit as a fraction to then say 4.5 times 10 to the -2 grams over centimeters cubed. And again, we're going to convert this unit fraction, so grams over centimeters cubed, into standard units. So grams again needs to go to kilograms, and centimeters cubed, well, the centimeters needs to go to meters, so we need meters cubed. Okay. Well, the grams, again, firstly, 1,000 grams is 1 kilogram. So therefore 1 gram divided by 1,000, we get 0.001 kilograms. So 0.01 kg on the top. Then centimeters cubed to meters cubed, right? So again, with these sort of squared factors, squared units, let's consider, so it's to do with volume, right? Centimeters cubed, meters cubed. So again, if I consider, firstly, a cube, right? Let's say I make all the sides 1 centimeter. So 1 centimeter by 1 centimeter by 1 centimeter. The volume is then going to be 1 times 1 times 1, which is just 1 centimeters cubed, right? If I consider the same cube, but now I'll convert the centimeter into meters. Well, 1 centimeter is 0.01 meter, because again, 100 cm is 1 meter. So therefore, 1 centimeter is 0.01 meter. So 0.01 meter by 0.01 meter by 0.01 meter. If I times these lengths, then the volume is going to be 0.01 cubed, right? So if I work that out, that would be 1 times 10 to the minus 6 as it's meters cubed, okay? And so so therefore, again, because the cube is the same, just different length, just different units for the length. So therefore, 1 centimeters cubed is 1 times 10 to the minus 6 meters cubed. That's my conversion. Alternatively, instead of doing this whole cube business, finding this cube here, what we can again say is 1 centimeter is again 0.01 meters. So what we can just do instead is just skip this whole thing and just basically cube both sides of this conversion. So then centimeters comes to centimeters cubed, and then we get 1 cubed centimeters cubed is 0.01 cubed meters cubed. So then if we just simplify a little bit, 1 cubed is 1, so 1 centimeters cubed, and then 0.01 cubed is, well, 1 times 10 to the minus 6 meters cubed. So we get that conversion quite quickly, okay? So instead you can just do this approach to get your conversion for squareds and cubes, okay? So 1 centimeters cubed is 1 times 10 to the minus 6 meters cubed. This is my conversion. Let's have a get rid of this. Does it simplify? So if I do 0.01 over 10 to the minus 6, that's 1,000, okay? 1,000 kilograms per meters cubed. Which means the 1,000 is my conversion factor, so 4.5 times 10 to the minus 2 be times by 1,000 to get it into kilograms per meters cubed. So then if I do that, if I times 1,000 by 4.5 times 10 to the minus 2, I get 45. So 45 kilograms per meters cubed. There we are. Okay. Part F. Now we have 6.3 times 10 to the minus 3, is it? Yes, kilograms per centimetre squared. So again, as a fraction, that's 6.3 times 10 to the minus 3 kilograms over centimetre squared. And then we want to convert this unit fraction, so kilograms over centimetre squared. We want to say that by kilograms is great actually. It should be in kilograms. We don't need to do anything there. That's there. But centimetre squared has to go to meters squared. So again, we need to convert a centimetre squared into a metre squared. So again, to help me consider that, if I consider a square, that will give by 1 centimetre by 1 centimetre. The area will be 1 centimetre squared. The same square, but with now metres. So 0.01 metres by 0.01 metres. If I convert the centimetre into metres, that area now will be 0.01 squared, which would be 1 times 10 to the minus 4 meters squared. Okay, and again, it's the same shape, it's the same square, just with different conversions for the units. So the area will still be the same. So 1 centimetre squared is 1 times 10 to the minus 4 meters squared. That's my conversion. So it's 1 kilogram over 1 times 10 to the minus 4 meters squared. I believe that should simplify. So if I do 1 divided by 1 times 10 to the minus 4, I get 10,000 kilograms over meters squared. So now I work that by conversion. So that's 6.3 times 10 to the minus 3 kilograms over meters squared, right? No, sorry, it should be times by 10,000, sorry. So times by 10,000, lots of kilograms over meters squared. If I work that out, well, 6.3 times 10 to the minus 3 times by 10,000, I get 63. So 63 kilograms per meter squared. And that is my conversion. Okay, so let's finish up with this question about labelling forces. Again, similar to what we did earlier. So again, we just need to name the forces drawn. So firstly, we have this box again that's pushed along rough ground. If we remember when we talked about modelling assumptions last time, rough means it has friction. Okay. Now, the box is, if you imagine being pulled this way, it says the direction of motion is to the right, it's forward, right? So it's in the direction of this vector B here, force B. So firstly, again, there'll be weight pulling it down, right? There'll be weight, that's force C. And because the box is on a surface, there'll be a reaction force opposite the weight, keeping it up. Now, because the box is being pushed, it's moving forward, because it's on a surface, the force opposing on the surface will be friction. Okay? And then what's pulling it forward, in this case, it's just a driving force. Okay? There's a force that's pulling it forward, it's pushing it forward. So that's a driving force. Okay? Now, part B, we have a man swimming through water. So again, like what, it's going to be a driving force that the swimmer is just pushing itself forward. It's exerting a driving force. Okay, so the muscles are contracting in the swimmer that allows the swimmer to push forward. Again, there'll be a weight that pulls the swimmer down. But what's going to oppose the weight that keeps keeps the swimmer afloat is going to be buoyancy. Okay, not a reaction force, because it's not on the surface, it's on water. It's on the flat solid surface like a table, it's on water. And then D, okay, again, there's some force opposing the swimmer swimming forward. It's not air resistance, it's not in air, it's in water. It's not friction either, because it's not on sort of, again, a flat surface. That is water resistance. So we've got air resistance in air, and we've got water resistance in water, or might be called drag, a drag force. Okay. Now we have part C. We have a toy duck being pulled along by a string. So you can imagine the string is D here. Okay, the force D is the string. So again, so a force. So if the duck is being pulled by a string, the string has tension, right? So D has to be tension, the force in the string that allows the duck to pull forward. Okay, so it's not a driving force this time, because it's not the duck itself pushing it forward. It's being pushed by a string. Okay, which is D. So the tension in the string is pushing the duck forward, not itself. Okay. And if you imagine then, this rope, right, it's obviously, this duck is moving on the floor, right? It makes the most sense. It's not in the air or in water or anything like that. It's being pulled along the floor, right, from the rope. With that in mind, obviously, firstly, it's being pulled down by weight. And then because it's on a surface, there'll be a reaction force from the surface pulling, that keeps the duck above ground, right? And then because it's on ground as well, if you imagine the duck being pulled along the floor, as it moves ahead, there'll be friction from the floor trying to oppose the duck moving. Okay. This part D last, and we have a man sliding down a hill on a sledge. So obviously it's on a hill, it's a bit inclined, so it's not a flat surface, it's not completely horizontal. It's still a flat surface, right? The surface it's on itself is flat. It's just that it's like a ramp, okay? But with that in mind, firstly, again, there's a weight force that's pulling the guy down. And again, because it's on some sort of floor, it's on the surface, the guy with the sledge, it'll be a reaction force that's keeping it up on the hill. Then D, and then C, sorry, the other force, obviously the man is falling down the hill. So what's going to oppose it moving, because it's going to be the friction, okay? There might be air resistance too, so it might be plus air resistance. As the air is opposing, as it moves down, the air obviously the air in general will try to slow you down, but also the friction specifically from the floor, okay, from the hill, from the floor surface, when it tries to move through the hill will have a friction on the sledge to slow it down, okay. But there we are. So that is forces and the units we'll be working with. So again, you need to remember kilograms for weight or mass. You need to remember meters to do with length and distance, and time in seconds. Okay, we'll be working with those, and hopefully you have a good idea about just what the kind of forces we are working with. So hopefully it makes sense with how these forces act with what we went over. We will be using some of these forces quite a lot throughout the mechanics course, okay. But yeah, for now that's it. I'll see you next time.